In this illustration, we intend to calculate the bearing capacity of a strip foundation using more column plasticity and Drucker-Prager in the Abacus software. In this example, the bearing capacity obtained from more column plasticity and Drucker-Prager have been compared with a Terzaghi solution. In the right diagram, you can observe the bearing capacity obtained from more column plasticity, Drucker-Prager, and Terzaghi solution. The soil and a foundation have been simulated in form of two-dimensional plane strain, in which the height of soil is 20 meters and its width is 40 meters. The foundation is made of concrete with a width of 2 meters and depth of 0.5 meters. I will enter the Abacus software for simulation. I'll click on Create Part. Here I intend to create geometric shape of soil. I will select the modeling space as two-dimensional, then select Deformable and Shell, enter the rough size of the tracing page as 100 and continue. I'll draw a square and enter its length and width equal to 20 meters. Then click on Done. Then I click on Create Part. Here I intend to create geometric shape of foundation. Select the modeling space as two-dimensional and continue. I'll draw a rectangle. Enter its length equal to 1 and width equal to 0.5 meters and click on Done. I'll enter Property module, click on Create Material. Here I intend to define the properties of soil using more column plasticity. I'll select Density from General menu, enter the density of soil equal to 1920 kilogram per cubic meter, then select Elasticity and Elastic from Mechanical menu, enter Young modulus of soil equal to 182 megapascal and enter Poisson ratio as 0.3, then select Plasticity and more column plasticity from Mechanical menu, enter Friction angle equal to 25.5 degrees and dilation angle as 0.1 degrees. Then I'll enter cohesion yield stress equal to 1 multiplied by 10 to the power of negative 5 Pascal and enter ABS plastic strain as 0. In this question, you should consider that the soil is quite dry. Then click on OK. Here I'll make a copy of this material, name that Drucker-Prager, and OK. Then I'll click on Edit, delete more column plasticity, and then select Plasticity, Drucker-Prager from Mechanical menu. Using this formula, you can calculate friction angle for the plane strain soil, and here phi prime is friction angle in the more column model, that is equal to 25.5 degrees, and here beta is equal to 35.86 degrees. enter flow strain ratio equal to 1 and dilation angle equal to 0.1 degree. Then I'll select Drucker-Prager hardening from sub-option menu. Here select shear and enter yield stress equal to 1 multiplied by 10 to the power of negative 5 Pascal and ABS plastic strain equal to 0 and OK and OK. I'll click on Create and here intend to define the properties of concrete. I'll select Density from the General menu and enter Density equal to 2,350 kilogram per cubic meter. I'll select Elasticity and Elastic from Mechanical menu. Enter Young modulus of concrete equal to 21 gigapascal and Poisson ratio equal to 0.2 and OK. I'll click on Create Section. Select Solid, Homogeneous, Continue. Here first we'll solve the question using more column model. Then in the second step we'll solve that using Drucker-Prager model and then compare them together. OK. Again, I'll click on Create Section. Continue. And here select Concrete Material and OK. I'll click on Assign Section, select Foundation, Done. And here select Concrete and OK. I will click on Assign Section, select Soil, Done. Here select Soil Section and OK. I will enter Assembly Module, click on Create Instance, enter Foundation and Soil into the Assembly section and OK. I'll click on Translate Instance, select Foundation, Done. First select this point and then this one and OK. I'll click on Translate Instance, select the whole of the model. First select this point, then Coordinate System and OK. This question will be done in 2 steps. In the first step, the weight of soil and foundation is applied, and in the second step, a vertical displacement is applied to the foundation. I'll click on Create a Step. Here select Dynamic Explicit and Continue and OK. I'll click on Create a Step. Select Dynamic Explicit and Continue. The nature of this question has a quasi-static form, but here we use Dynamic Explicit Step for it. We should consider the time period of step too long. So here I'll enter time period equal to 100 seconds in order to keep the quasi-static nature of the question, and OK. I will enter interaction module. Here we should define the interaction between the foundation and soil. I'll click on Create Interaction Property, Continue, select Normal Behavior from Mechanical menu, then select Tangential Behavior from Mechanical menu, then Penalty, enter the coefficient of friction equal to 0.5 and OK. Then I'll click on Create Interaction. Here select Initial Step, then select Surface to Surface Contact and Continue. I select the below surface of foundation, Done. Then click on Surface and select the top surface of the soil, Done. and OK. In the next step, I'll enter Load module. Here I'll return to the Part module, select Partition from the Tools menu, then select Face and Sketch. Draw a vertical line in this manner and enter the distance between these 2 points equal to 1 meter, and then click on Done. I will enter Load module, click on Create Boundary Condition. Here select Displacement Rotation and continue. I'll select the bottom of the soil, Done, and close the boundary condition of U1 and U2 for it, and OK. Then I'll click on Create Boundary Condition. Here select Displacement, Rotation and continue. I will select this line, then this one, and Done, and close the boundary condition of U1 for it. Here you should note that the line having been displayed by red color is the symmetry line, and the model is symmetric to this line, and since the model is symmetric, we simulate only half of the model in this question. In the next step, I will click on Create Load. Here, select the Gravity Loading step, then Body Force and continue. I'll select the whole of the soil, Done. Here we should apply the weight of soil. Here, since the soil is dry, the effective weight of soil is equal to 1920 multiplied by 10, and OK. In this manner, the weight of soil is equal to 19,200 Newton per cubic meter. I will click on Create, then select Gravity and continue. I will enter the gravity of Earth equal to -10 meters per second squared. Click on Seed Edge and select Foundation, Done, and OK. In this manner. In the next step, I will click on Create. Here, select Pressure and continue. Select Top Surface of Soil and Done. Here, we should apply the overburden pressure. Here the overburden pressure is calculated according to this formula in which gamma is the specific weight of soil, dF is the thickness of soil above the foundation level or the same depth of foundation. Actually, in this question, we will not simulate the soil around the foundation, but we will apply the effect it has. Here, I'll enter the pressure equal to 9,600 Pascal, and this pressure is caused by the soil around the foundation. I'll click on Create Boundary Condition. Here select Step 2, then Displacement Rotation and continue. I will select the top surface of foundation, Done, and enter displacement equal to -0.3 meters. Then click on Create Amplitude and continue. I will enter time period as 0, amplitude as 0.2, time period as 100 seconds and amplitude as 1, and OK. Here I'll select amplitude 1 and OK. Here I'll save the model. and OK. I'll click on Create Predefined Field. Here select Geostatic Stress and continue. I will select the whole of the soil. Done. Here we should apply the vertical effective stress since we can calculate the vertical effective stress of soil using this formula, in which gamma is the effective weight of soil, Q is the overburden pressure, and dF is the thickness of soil above the foundation level. The vertical effective stress on the top surface of soil is equal to negative 9,600 Pascal, and this quantity is the same overburden pressure. And the vertical effective stress in a depth of 20 meters is equal to negative 393,600 Pascal, and the lateral coefficient is equal to 0.57. I'll click on OK. I'll enter Mesh Module, click on Seed Part, enter Approximate Global Size equal to 0.5 meters and OK. Then I'll click on Mesh Part and Yes. Click on Seed Part, enter Approximate Global Size equal to 0.5 meters and OK. Then I'll click on Mesh Part and Yes. I will click on Assign Element Type, select this soil, Done, and put the element family on Plane Strain. Put Element Library on Explicit, and OK. I will do the same for Foundation, and OK. I'll enter Job Module, click on Create Job, Continue, OK, and click on Submit. The analysis was done successfully, so I'll click on Result. Here you can observe the deformation of soil. What you observe here is the half of the model. If you want to observe the whole model completely, first click on Create Coordinate System. Here select System following a single node and continue. Then I'll select this node, then select ODB display option from the View menu, and then click on Mirror Pattern tab. Here select CSYS1, then I'll put mirror planes on YZ, and click on OK. And here you can observe the full model. Here we intend to calculate the bearing capacity of the strip foundation. In this picture you can observe the bearing capacity calculated using the Terzaghi solution, and here the formulae and the relations have been written, in which the final loading capacity of the strip foundation using Terzaghi solution is equal to 249 kilopascal. To calculate the bearing capacity of the strip foundation using the Abacus software, I'll click on Create XY Data, select ODB Field Output and continue. I will select Unique Nodal, deactivate the step 1 and OK. I'll select the vertical stress from here. Then select this node and click on Save. Then from here I'll select vertical displacement. Then select this node and click on Save. In this manner, here you can observe the vertical stress under the foundation center, and here the vertical displacement can be observed. I click on Create XY Data. From here on Operate on XY Data and Continue. Then I will select Combine, select U2 as the x-axis and S22 as the y-axis and click on Plot. I will put a negative sign here, then one negative sign here and click on Plot. I will right-click on the diagram, Edit, select these two columns, copy, and paste them in the Excel software. The first column is displacement, the unit of which is meter, and the second column is vertical stress, the unit of which is Pascal. Here I will right-click and select the Select Data, then click on Add. Select this column as the x-axis, select this column as the y-axis, and OK, and OK. The bearing capacity having been calculated using the Terzaghi solution has been distinguished by Brown, and the calculated bearing capacity in the Abacus software using more column plasticity has been drawn by blue color. I will enter Abacus software. This time we intend to solve the question using Drucker-Prager model. From here, I'll select Drucker-Prager model and OK. Enter job module. Click on Create. Continue. OK, and click on Submit. The analysis was done successfully. I'll click on Result. I'll delete the extra diagrams, then click on Create XY Data, then select ODB Field Output and continue. Here I will select S22 and U2, then select this node and save. After that, I'll click on Create XY Data. From here on Operate XY Data and continue. I will select Combine, then select U2 as the x-axis and S22 as the y-axis. Put a negative sign here, another one here. Click on Plot and Save As. Then I'll click on Edit, select the two columns, copy, and paste them in the Excel software. Here I will click on Add, select this column as the x-axis and this one as the y-axis. Here the calculated bearing capacity using Drucker-Prager model has been distinguished by red color. Here you can compare the outcomes obtained from the Terzaghi solution with those obtained from Moore column and Drucker-Prager models, and as it is clearly observed, the calculated bearing capacity using the Terzaghi solution is equal to 249 kilopascal, and the calculated bearing capacity using Moore column model is equal to 450 kilopascal, and that having been calculated using Drucker-Prager model is equal to 400 kilopascal. Here, if you intend to get more accurate outcomes, you should use more points in order to define cohesion properties of Moore column model and define more points as well. Also, if you intend to have more accurate outcomes about Drucker-Prager model, you should use more points in order to define the hardening behavior of Drucker-Prager model.